Now we're gonna do oh sorry. We're gonna do real proof and lean. So let's go to let's open VS Code again. Um we can open folder, we can open the workspace from the file. We're doing, oh, we should probably delete this because it has like mathlib. Um so now we can open this. This is our lean. We can just check that lean is working with this test file. Oh, we're waiting for lean to open. Let's just wait. We can move our basic natural numbers file here if we want. So we can just do, I don't know, we can organize the names of our files later. I don't really have a good idea right now, so I'm just gonna call it, um, what did I call it over here? I called it, okay, that's the name of the file. Um, the name of the file is vertical asymptote. Cool. So what do we need for this? Um, so I'll tell you like what I think the way people develop lean or usually do. So usually, um, they already have a proof in mind in paper. And the first steps, so we're gonna probably skip a few of those struggling things now because I've already done them. But in future sessions, we can record like the process of formalizing things entirely without knowing even how to formalize the concept that we have in intuitively in mind. But vertical asymptote is not like, so like the first step would be, so the proof we want to do is this theorem. Limit, so the limit of, so I've already made some simplifications before coming because I knew they were like distracting. So we have some function from the right side and we approach it and we go to plus infinity. So this simplifies the proof enough that if we're just learning lean, we don't have to deal with absolute values because we're only going for from the right. But we do have to learn what infinity means. So the first thing I did actually is I defined infinity the way Rudin does in his analysis textbook. He called it the extended reals, and the main operation that he did was x plus infinity equals infinity. That was like the most crucial step because with the definition that I was going to use was just the standard epsilon delta definition. You guys have seen that, right,
Yeah. Yeah.
Emily?
Yeah, yeah.
So like the standard definition would be like for all epsilon, okay, for all epsilon um greater than, okay, perfect. So for all, basically, for any given arbitrary closeness to the like approximation to the function or closeness to the function, we can get sufficient for, there exists some sufficiently large, so sorry, sufficiently small in this case, sufficiently small delta such that we can get close to C. So we're like in this neighborhood, and so that we guarantee that we're within epsilon. Oh, interesting. I already did a mistake, I think. But let's see. So this is like the definition. So I defined L to be infinity, and then I tried to use this proof. And well, the first thing I realized, I usually like by hand by paper, sometimes I just go to the goal and see if I start from the answer, and I know more or less I have all of this stuff in the hypothesis space. I know this stuff. How do I like link them? Sort of like what we call in CS like bidirectional breadth for search. So we have that. So this, let's just consider some epsilon. I don't know, any epsilon greater than 0. So consider some epsilon greater than 0. And then what did I do? I did um I did this, and then this jumps to infinity no matter what, right? So it's never bounded by epsilon. So I just sort of realized that this, like basically the reason I'm showing you this is that you will realize that formalization is not like easy, basically. Does that sort of make sense? So I decided that I guess I could have like tried to fix, so by including infinity into the real numbers, I could have like maybe, I don't know if it would have worked, but I'm not a math major. I'm a math minor, so it didn't seem productive to try to redefine fields and groups and all of the things that like the fields and will real numbers exist and make it work. So instead, I just Googled enough. I forget exactly, maybe I forget if I asked GPT-4 or if I just Googled it, but eventually I came to realize that the definition for unbounded limit exists already. So this formalization doesn't seem promising. So I moved on to redefining limits themselves. Um, or like defining unbounded limits basically properly. So I went to this thing and I defined what this means. And actually, the intuition, now I remember where it came from, but I remember doing some sort of probably analysis class or something, or some philosophical discussion maybe of what infinity means. And it just means it can keep growing, right? If you stop at some point, there's something bigger. So eventually, either that realization made me come up with like this definition, basically. Sounds sort of then this actually looks like something that can be formalized because this is a real number, delta x, none of this looks like strange. Any questions? This
Yeah,
looks
so instead of playing around with the epsilon delta definition of the limit, you show that the limit, I guess, is unbounded.
right. I basically read, well, I don't know if I did it. I just like I realized that this was more promising,
Yeah.
basically.
I think
Okay, that
that's
makes sense.
yeah, because for the regular epsilon delta definition, they assume that the function converges, but because this one diverges, you have to use a different definition, which is this one.
Basically, yeah, like the
Yeah,
definition assumes that L is a real number.
yeah.
Um, yeah. So that's it. Some things that I'm already noticing about this definition that I can't really easily change right now. I can try. Maybe this is not a big deal, but I can say I'm just gonna make it look like lean, a little bit more like lean now. Um, and some of the changes I'm doing is because if you remember, my friend Scott from the Lean Prover at Stanford reminded me that, or I didn't know this, that sometimes there's conventions in MATLib, and to have the proof be like flow more naturally, you can redefine things. So next formalizations we do, might have to redo our formalization as we go into proof, because we'll see some proof call that is annoying to deal with, and it's just easier to change the formalization. I mean, I guess you could also during the proof like redo rewrites or whatever. But I just know that right now less than or equal is nicer and it's used in MATLib. So I'm just gonna try that. I don't know. Yeah, so I'm just gonna switch everything to less than or equals. And basically the definition is simple, right? So like the definition of unbounded limit is so unbounded limit means um, for any m, um, we can there exists a close sufficiently close x such that f of x is strictly strictly greater than the target m. Cool. I think that seems like maybe I'll just move this out. Cool. So, okay, so this is more or less the process for formalizing things. Let's see, is there anything that I should say or that we should say? Oh, maybe one point is I was wondering as I formalize this, what if it should be less than or equal or less strictly greater, if it should be greater than. And then I realized that if it's infinity, you need to really keep growing, right? Because otherwise you can just stall at m. So I think that's a reason for doing it with less than or equal. If you guys have any comments, feel free to make them at any point.
I think in this case, because it's a for all m,
Yeah.
less than or equal to is equivalent to less than. Because you can just choose a bigger m, and then you get something that's strictly greater than your original.
You can choose a different a bigger delta, right?
I see. Yeah. It's also like an or statement, right? Like less than or equal. Let's see.
Yeah,
You only need to make one of the two equal. Let's see. Um,
But I feel like strict inequality might be easier to do in this case, or else you would need like any
actually,
case.
wait, I think non-strict inequality is a weaker statement, so it'd be easier to prove. But I think in this case they're equivalent, so you could do either one.
Sounds good. I also don't think this exact detail matters for learning long.
Yeah.
So, but it is important for like formalizing things properly.
Mathematical pedagogy.
Yeah, yeah. I'm sort of assuming I'm a more of a lean developer, so I think my assumption is that the people that do math are doing math correctly. Um, I'm just trying to help the formalization, like making formalization easier or more fun and pleasant. Cool, let's do this. So I think one of the ways to do theorem proving is in lean is that you already have a proof that you understand pretty well. So by hand in pen and paper. So this proves so maybe let's just start naming things. Try to make it look like pseudo lean. So um maybe reciprocal. Is that how you spell reciprocal? Like an is it with an I or with an A? Reciprocal or reciprocal?
I
Okay.
think it's reciprocal. Yeah, you have it right.
I think this one looks more correct.
Okay. I'm a little dyslexic. So
Yeah, this one's correct.
reciprocal of this is why I like GPT-4. Maybe it doesn't help me with my dyslexia because it doesn't force me to learn the syntax. But reciprocal of x, um, okay, maybe limit of reciprocal of x is unbounded. Is unbounded. Cool. So that is our goal. So I'm just gonna show you how I did the proof, and we're gonna try to translate it to lean. So first we know what the definition that we're going for is. It's this one. Um, so yeah, so this is the definition. So let me think about it. What did I do? So intuitively the way, okay, so first I consider some m greater than 0, right? I sort of know this should be some sort of intros, I hope. Um, intro m or something. Um, then what I did was, okay, there exists some delta. So if there exists some delta, we just sort of want to show that either this statement is true with some sort of logical argument, or just choose a delta and show that it works, basically. And the way I chose the delta, I guess it's sort of obvious. I want to show this is true. So I know that, so first, like, choose a delta. I know that I want this to be true. So I sort of know that I want 1 over x. So I want, sorry, m to be, I'm just gonna switch it to less thans. LT is might be the lean um naming convention for less than. And I know I want this, so this is like the delta I want to go for, basically, right? Um Actually, lean doesn't like, so you will see that I already made this mistake. I don't know if it's a mistake, but I already know that lean will try to force me to write this because I'm doing this notation. I'm doing the proof, and it keeps rewriting my symbol to this. And Brando doesn't know if this symbol is like equivalent Or if I don't want, like, I don't know, it's lean is like strongly suggestion that I should be using that symbol instead, you know? We could have seen that in the proof if we developed it from scratch. But this is like this notation I'm gonna use. So
I think the 1/m has to be greater than x because you have
did
to
I
flip the inequality.
did I do
Or
something?
1/m.
Yeah, of course.
Yeah.
You
No,
multiply.
no, no, no. That
No, it should
the
be.
m is yeah.
I'm starting
That
to
should be less than, and then the 1/m should be greater than x.
So
So like
the
on the
second to
third
last
step.
method. Oh no, that one should be correct. The
Oh,
one you
that
just
was
changed.
just from folding the definition. Sorry.
Yeah.
Yes. And
Apologies.
then this should be greater than, yeah.
And switch to the next one.
Or I guess you would want to switch the order
Yeah.
of the two.
Yeah. We can switch it here. Sorry, guys. Being careless.
It's okay.
Usually, yeah, cool, awesome. So you get, and this makes a lot more sense, right? Because we know that X. Actually, had already noticed when I was talking that something was weird because I didn't see. Okay, actually, we have to remove this definition because we're doing it from the right to avoid the absolute value function. So I'm just gonna remove this. Okay, so yeah, I was already noticing that it was saying greater, and but I knew that we were going closer to zero, not farther away. So something was wrong, but I was sort of saying some other thing about lean, I think. I forgot what I just did. But cool, let's keep going. So we know like we just say delta, oh wow, delta equals perfect. And then we just okay, so I guess we need to show that delta is greater than zero. Um, let's see. This is sort of, at least for us, is obvious because m is greater than zero. So first we show this. Let's try to show that. Oh, it doesn't like that. Change the color. Okay, so maybe we can, I don't know if pseudo lean will work, but that case, we want to show that. So we know the fact, so we know m is greater than zero, and we can sort of guess that there's some sort of theorem in lean that looks like this, right? So that looks like this in the sense that if there is m is greater than zero, then it allows you to just sort of flip it and it remains true. So by some theorem, in lean, I assume it actually. I wonder if GPT was already division by positive number. By lemma in lean. Maybe this is the name of the theorem, but we can figure that out later. Cool. So that is true. Okay, so now we have to show this, right? Oh, sorry, we have to show this, um, assuming this. So at this point, I'm just gonna do the proof going forward. In lean, we can manipulate either side as we want, as we will see, but I'm just going to write it going forward. So we have this. So C is zero. So we need to change our statement. Maybe we can just 1 over x goes to plus infinity plus zero. So C is zero. So we're probably going to do some sort of rewrite, I think, to show, maybe I'm thinking already too much in lean, but maybe it's because I already did the proof. But this is sort of, we want this. This is just sort of like an assumption. Um, yeah, C is zero, so we just choose an x greater than zero. So this should be true for all x. So maybe there's like one more for all x in this neighborhood. Okay, cool. Okay, cool. Okay, nice. Let's use the other side. Oh, sorry, I sort of deleted it. And yeah, let's grab it. Okay, this is probably just going to be the same rewrite rule somehow. X is less than. Okay, let's just use the delta. Cool. Awesome. So we have this and we want to show that this is true. So we want to show, so this is sort of in brackets for Brando to remember. Oh, want to show. I'm just gonna unfold the definition. This is what we really want to show, right? Cool. So how do we show it? So I'm just gonna put this here so that we know we have these facts now. Okay, so we have this in our assumptions, right? So what I'm gonna do is multiply both sides by x inverse. So at this point, as I'm doing this proof by hand, I might be thinking, okay, either I'm gonna need a theorem that helps me do this, or maybe Lean's automation is really good and I can skip steps, you know? Like we know this is gonna be like um 1, right? For example. So maybe this transition is sort of maybe like by so multiply oh multiply both sides by x inverse 1 over x if x over 1 over x is greater than 0. So this actually makes me think that we are gonna need to do use this fact to show that it's positive, right? We already did that somewhere, I think. Did we? Okay, by this lemma, right? So we're gonna probably reuse this lemma a couple times. We're probably gonna reuse it here. And
Oh,
yeah,
on line 35,
yeah.
should it be m inverse times x inverse? Because we multiply both sides by uh x inverse, right?
Sorry. Yes, it is. It is. Oopsie. Sometimes me typing. Oh, and then yes, that is correct. Cool. So now, um, by identity of fields, so probably lemma and lean, some sort of lemma and lean, or automation. One of the two will either do like automation, will do like a lot of steps for us, or it will do like the one step we want to do. So this is okay, cool. We have this now, right? Okay, Copilot doesn't know how to do algebra. Okay, fine. Thanks for not being helpful, Copilot. Okay, cool. We have this. So now we're probably going to do the same fact, but multiply both sides by m. So I bet we're going to have like two lemmas that allow us to do this or something like that. Okay, so we're going to do this, but now the multiplication will be on the left side.
Wait, I think that should be
Oh,
m
did I make a
inverse,
mistake?
right? It should be m inverse times x inverse.
That
Yeah,
it is, no? Sorry.
it's m times x inverse right now.
Oh, did it become something else magical? Oops. Was that a mistake by Copilot? That's not good. So be careful with Copilot. Um, I know it can't really do logic, but it can do my autocomplete.
Yeah.
And I don't want to type as much. Um, okay, so multiply both sides by m then. Actually, this doesn't probably this I think this will need a lemma. So we're going to do some sort of like half statement in the proof. We'll see what that means. And this doesn't require anything because that's true by this at the very top, right? That is like some sort of assumption we introduced at the beginning. Cool. Okay, let's do it. We have this, and then we do identity again. Okay. Um, and that is exactly what we want to show, our goal, right? The right-hand side of the implication. So QED, I think. Do we think the proof is correct? At least the proof by hand?
Looks good to me.
Yeah,
Excellent.
I think it's good.
Awesome. So now let's make this. So I'm gonna try to leave this on the left, and I'm gonna try to make I'm gonna make this. I wonder how to. I'm not 100% sure it will have space. So let's experiment. Okay, let's just continue with the proof now. Now to write it in math in lean. So the first thing that we need is to import. I wonder if Copilot can help us import real numbers from mathlib. I don't think this is right. Yeah, I knew this wasn't right. Luckily, Brando is going to cheat and look at his. Okay, so maybe we don't have to cheat. We can just try to see how Brando would figure it out if lean wasn't available. So I would choose. There's different options. First is like the lean documentation. Um, yeah, this one. I'm just gonna see real numbers, real numbers. Okay, this doesn't look easy to traverse. So I'm just gonna ask Google to do the search for us. I've had better experiences with Google search. I think this should work. Uh, um, mm, is there some sort of basic data dot real dot ba I know that that's not quite right. So okay. Okay. Let's see if Moogle helps then. Real numbers. It also found that. I don't remember why I'm trying to import this, so I'm just gonna ignore it for now. I'm just gonna define what we need. So we need the definition of f, right? And I know that lean will prefer this notation already, so I'm just gonna define it like that. So we define a function from the reals to the reals. Cool. It doesn't like something. What's wrong? Expected token. I don't know what that means, so I'm just gonna do 1 over x. Failed to synthesize. Okay, I know what
Oh,
it's doing. Oh, do you know why?
I think you need a
I
name for the
s-
function.
no, I suspect that it
Oh,
thinks you're dividing one, which is a natural number, by x, which is a real number, and it doesn't know how to do that.
Oh, it might be doing that. That could be doing it could be doing that. Um, more messages. Expected. This is not a very useful error message.
Yeah.
I'm gonna I know okay, so I'm gonna give you an insight that already some experience that I have. I don't know if this will be the issue now, but 1 over x is not like real numbers aren't computable, right? Um,
Mm.
because they're like some sort of infinite Cauchy sequence. So I don't think you can prove things about them, but you can compute them. So I know this, and there's also like 1 over something. So there's like a point where it won't exist. So I know that you need to write non-computable. That didn't fix the bug. So we're gonna just to make this quick, because we do need to finish at 2:30, where I'm just gonna quickly check what this was the issue. Okay, it is working here. So my assumption is that the import didn't work. Um, yeah, we should have gotten this import. But let's see, why didn't we real numbers? So import real numbers mathlib. Okay, this looks a little better. Real. This is what we want. real basic lean. Okay, mathlib data real basic. So we need to do this import. Mathlib data real import. Mathlib data real basic. There we go. Now it worked. I'm not 100% sure why we needed that, but it would be nice to figure it out. It would be like one of those questions that I would ask in Zulip. The reason I'm
Wait,
confused is because, let's see, if I uncomment everything and I try to check the type of R, does it allow me to do it? Okay, unknown identifier. Okay, cool. That's how I would have known that I needed that. It doesn't know the type of R, and R should be of type. Cool, great. Now it works, and that's how you would know that you needed that import statement. Sorry, Eric, you were saying?
oh, could you try 1/x? Because I want to see if the natural number thing was the reason. Or
Yeah,
if,
I think this is called type coercion, with the thing you're worried about, which is a very sensible question. Um,
oh, looks like it still works. Okay.
yeah, let's do let's check it. Cool. It is from a function from R to R. It should be R. Great. It shouldn't allow eval. Yeah, it doesn't fail to compile definition. Consider marking it as non-computable because it depends on F and it does not have executable code. Yeah, cool. We know that. Actually, we could. I wonder how the code looks like. Oh, okay. It just sort of knows somehow that X inverse is not computable. All right, we're going to print the proof term. Oh, I guess that is the proof term. Duh. Sorry, there's an equivalence between functions, and sometimes I think of definitions of functions as like proofs. So like the types is the theorem, but this is like the proof of some theorem, and this is the theorem is R to R, I guess. If you ever want to prove, I wonder if we can do that proof just to show you. Okay, I'm gonna comment that just to show you theorem, um, any R. So R to R. Can we just do F? Oh, by F? No, exact F. Ah! Come on, let me just write F. Theorem. Okay. Huh. I wonder if it lets me do that. Well, it's not letting. Okay, it's some function from R to R. Okay, this should work, I guess. Interesting. I'm not exactly sure why this is not working. We can do this as homework later. Okay. Anyway, let's continue. I like to do like some small like unit test of my definitions to make sure it works the way it works. So I'm just gonna do f of 1 should be 1. Yeah, f of 1 should be 1, and it worked. Cool. It just simplified, right? It had f and it just made it oh, wait, it just used the definition of f and simp. Great. Okay, that is simple. Let's do what about 2? Maybe this one should be, does this work? Okay, this also works by simp, right? Cool, awesome. Um, I wonder if we can show, just for the sake, f is equal to f prime. Does it, okay, it doesn't, so by, we have f equals, oh, no. So for all x that are reals, f of x equals f of x. Sorry, add x, r is true. Ooh, that does not look like something. Okay, maybe the type is wrong. Okay, we have the goal. Here it is. Can you just simplify both? Woohoo! It did it. Okay. Okay, I think that's enough for unit tests. So now let's just try to define limits of reciprocal or like unbounded limit, and then we use that definition to do our theorem. So that is the way I would do it. So I would define, and the reason is that when I was formalizing this, it took me like a lot of effort to figure out what the formalization of unbounded meant. So it made sense to me to just start with that. So that is an unbounded limit. So unbounded limit. So actually, let's not have Copilot do it for us. We know that we want to do this, right? We want to formalize this, right? And that is equal to the definition we have above, right? Cool. So this is what we have. Let me see. All looks good to me. Okay. So if we look at the left, this is really just notation for a function. Like unbounded limit is a function that takes f and c. That's it, right? And it tells you if it's true or not. Like it's a proposition about f and c, sorry. Does that make sense? So the definition of unbounded limit should be a function of f at c with um the type that it should be a prop, right? This should return a prop. It's a proposition, and it should be, I'm gonna go,
Is prop just like true or false?
no,
Or
that's a
how
great
does prop
question.
work?
Prop is like, that's a great question. If prop was just true or false, that would mean that, okay, so this is actually like a deep thing about lean and calculus of constructions. Um, True or false, if you have a function that evaluates to true or false, it means that there's an algorithm that leads you to true or false, right? Like you can compute it and return 0
Mhm.
or 1. Okay, prop is a proposition. So it's like some sort of, remember when we defined inductive types previously,
Mhm.
like inductive nats, um, with constructors? Like, so I wonder if we can look at the definition. Oh, okay. Well, this wasn't super helpful. I was hoping there would be like some sort of um inductive definition of prop. But if you take like a programming language classes, you will have this, which is like true. They're called true. I think people call it hat actually. I don't remember how they do it, but it's not actually true in the sense of like a value that you arrive at. It's just like a constructor. And I guess if it's false, okay, the main point I'm trying to say is that it has constructors. Okay, I think those are all you need to do everything, but I'm gonna keep writing. Oh, maybe it might only define the ones. Yeah, somehow Copilot knows what is like complete, not complete, but yeah, I guess it complete. You only need and or not, right? Implies is like a function of um it's defined in terms of these, etc. Why is it angry at this? Prop expected identifier. I'm not sure what the issue is. I'm gonna comment it out. But the answer I'm saying something convoluted. I'm being convoluted, but the answer is there's a difference between computable booleans and props that are just statements that have proofs or are false, and then you can't compute them. Something like that is the difference. Great question. We should
Wait,
maybe
so is this like even if it's true, it's not necessarily true that you can make a proof for it?
if it's true, okay, that is a logic. Okay, there are differences between what's true and what's provable. Those
Mhm.
things are different things. That's why there's like a Gödel incompleteness theorems. There's true statements that don't have proofs. So I probably shouldn't have said the word true. What I probably should have, it's about provability. What I'm really trying to say is that a Boolean function you can use an algorithm to arrive at true or false. That part makes sense?
Hmm.
Okay. Um, but there are statements in mathematics that are like there's true statements that are unprovable.
Yeah.
So that's
So
the
are
difference.
those the reason that
That's the
like prop?
Yes, that's the reason prop exists,
Okay.
basically. And the thing I wrote here is more like syntax stuff that I wanted you guys to know about possible implementations of prop. Actually, I'm going to
Hmm.
try to inspect the constructors of our formulas as we go forward. Actually, I think we can already do it here. If we do unit, and then I go here, and then, oh, look, it already okay, no. Okay, if I hover over and for all, okay, let me see the definition of for all. Okay, look, okay, look, it says at ec r f x f prime x of type prop. What this means is equals. Remember how we did an infix notation? It's telling us what equals means. Equals is a function, um, and it's taking f of x on one side and f prime of x on the other side, and it's returning a prop.
Oh.
The reason there's an at is that the equality has something called implicit arguments, um, or parameters. I forget now the difference. We talked about it yesterday, but if you remember which one's which, remind me. I don't remember, but so the implicit arguments is saying equality is receiving in its implicit argument the type R. So if you think about it, equality could be equality about nets, rationals, or whatever, right? In this case, it infers what it is because we have f. F is a function real, so the implicit argument is given to the function automatically. But if you want to explicitly given, you need this at. Does that make sense?
Wait, sorry, you cut out there for a second for me. Could you repeat that?
Yeah, what I'm saying is that equality is, we can actually jump to the definition of equality. Equality
Uh-huh.
is a function that takes alpha, um, and maps something to alpha to prop. So
Hmm.
actually, it's not showing the implicit arguments. That is, I thought it would. Actually, there it is. Somehow, I don't know. Sorry, I'm just sort of looking through. Okay, so if I hover over ec, it says these squirrely brackets. Do you see them?
Hmm.
So what that means is that equality actually receives an implicit argument.
Oh.
Like lean computes an extra argument that the user doesn't usually see because it's obvious. It's like an implementation
Hmm.
choice of how you implement equality. The
Yeah.
developers, so at makes forces you to give that implicit argument explicitly. In this
Oh.
case, in this case, when it shows us what equality is, it shows us that it's R, the real numbers, because
Mhm.
it inferred it from F and X.
I see. So
Um,
ec can um so the first thing is a type, and then that's
yes.
usually you don't have to specify what type of equality you want to use because it's obvious from what you're trying to make equal.
Mm, I don't want to say usually. So like people define functions however they want. If
Hmm.
like your answer is yes, but you usually don't pass the type argument in equality because you know what sort of world you're talking about, I suppose.
Hmm.
Yeah, yeah, that's it. So you can hover over things in your proof state and like look at how they're constructed. And that gives you hints on what tactics to use. I don't know why it doesn't let me see the constructor of for all, which makes me sad. Maybe somebody that looks at the video on YouTube can tell us um, if they reach at this point. But I think let's move on with the proof. I think the question was great. To get a real answer is let's look at theorem proving manual that Leonardo has made for everyone some other day. But for now, we're just gonna accept that prop is doesn't allows us to express any mathematical statement without violating like computing proofs that aren't computable or something.
Mhm.
So this is our definition. Um, usually I won't. So Copilot already made a mistake. Yeah, yeah, it's something's not right. For all f, yes, this part is right. Okay, for all f greater than 0 implies, I think we need a 2. Why isn't it going to 2? Okay, I'm gonna
Oh,
delete.
I think do you need to remove the colon equals after prop?
Oh,
Or never mind.
I
Oh
don't
no,
know.
no, no.
I
That
just
should
got
be good.
I just got mad and I don't know what happened, but now it let me do it. So there should be a delta greater than 0. Yes, I think this is the right one. Interesting. I didn't know this would be syntactically valid. No, I don't know if this is, no, this is not the way I would do it. I think this is what I would do. Basically, for all m with this property, once we have that assumption, there exists a neighborhood there exists a neighborhood such that we can keep growing, right? So that is more or less what I'm thinking in my head. So there exists a neighborhood. Exists a neighborhood? Yeah. Anyway, there exists a neighborhood such that when you're in that neighborhood, um, f of x, there you can once you're inside that neighborhood, f of x can keep growing, right? It's unbounded, right? We can keep going on. For sufficiently large delta. Cool. So let's do it. Any questions? All of this looks good to me. Cool. Excellent. F of unbounded limit of f. So no information. Why is this no information? Limit or let's this is now the proof would be show one f so is unbounded or show 1 over x is unbounded or 1 over x has a vertical asymptote at x equals 0. Cool. So, okay, now it's trying to Copilot thinks it's lean too. I don't think that will actually work. I'm just gonna allow it. Yeah. So yeah, it doesn't. I don't think this is valid lean for syntax. Yes, it has commas. I don't think commas are valid anymore. Okay. I'm just going to. So we know that, but a byword gets us into unless we know the proof, like the exact function that has this type like this giant type. I don't know. I wouldn't be able to type that function in one go. I think it's easier to go into like function what do you call it? Tactic mode. Cool. The first thing is this is our goal, right? Just look at the goal, make sure that everything looks good. The first thing Copilot suggests is intros. I don't actually know what intros does versus intro. But for the sake of pedagogical reasons, I'm just going to tell it to unfold unbounded and f. So now we should have.
What does it mean to unfold? Is it just like,
Yeah,
yeah,
that's a good question. And you can always hover on the definitions, and it says for a non-recursive definitions, this tact is identical. Okay, that wasn't helpful. Unfold. Oh, great. Thank you. That doesn't help. So um I would go to the mathlib, the mathlib stuff, and say unfold tactic. I think it's not going to search well. Yeah, this is, I never find this search thing useful. I always do it by Google site search. Okay, tactic, this one looks better. I think actually, yes. So knowing what the difference between lean.elab and lean.meta probably is useful to be a better lean developer. I don't know the difference, but I went here and the definition didn't look useful. I went here and hopefully the definition is useful. No, it's not really. Okay. This is not really helping me. unfold? Is there like a unfold? Okay.
Wait, intuitively, it's just plugging in F and plugging in the other thing you told it to unfold, right? So
Yes.
like
Oh,
bringing it down to the basic definitions.
right. Unfold ID, unfold definition ID. Actually, I should have not jumped to the browser so quickly. It already told us here what it was. Unfold ID, unfolds definition ID. So you have a definition ID, just unfolds it. Like it just puts it in, like plugs it in, like what you said, Eric, basically.
Mhm. So does it like create the variables? Like, is this the same as like doing intro M? Like, or do we have to
No, intro does
create
something
M?
else. I'm just going through the proof in a little bit more granular level. So
Uh-huh.
if you just do this, look at this, Emily. This
Yes.
doesn't have for all statements, right?
Yeah.
What that
Oh,
means,
okay.
like basically lean doesn't know what that means, really.
Yes.
So
Okay.
so it has to, like, it's not equivalent to, well, we know it is, but you
Hmm.
need to show it. So
Yes.
lean has a very good automation. So I think if you do intro M, um, it's sort of already in, so it unfolded the definition and introduced M. You see that?
Yeah. Yes.
But it didn't
Yes.
unfold F actually. I wonder if I do this, what happens? Yeah, it doesn't, I don't know what that did, but it introduces a variable F. Oh,
Mhm.
interesting. Let me see what it does. Okay, cool, interesting. Okay, so just for the sake of pedagogy, I think unfold isn't done very often, but I'm just gonna unfold both definitions. And now we have the goal exactly the way we want it. We know that we already have the, like, the proof here, right? So we know we need that. So why not just unfold it immediately? Does that make sense why I did it?
Yeah. Yeah. No, that makes sense. That
So
makes
now
sense.
now here I know that I have a for all and a statement about that for all. So I'm just gonna introduce both of them. So I'm gonna say H M H pos, like it's positive. Cool. That looks like a sensible way to name your hypothesis, because naming is power, so we use good naming. Excellent. So now we know this. We want to show that for sufficiently large delta, we can get close to, we can get too big. We can make our function bigger than the current m, right? So we know that corresponds to this, right? So let's see. Before I went with Scott, I didn't know how to tell Lean to introduce delta, like to give a witness, basically. So I think I'm just gonna choose delta equals to this, and let's see if it creates the right tactic. Okay, this probably will only create like some sort of thing in the, yeah, in the hypothesis space. In Coq, this is called local context, a different theorem prover. So that didn't really change the goal. That's a problem. Um, yes, delta should be positive. Okay, but it didn't like, okay, something didn't work there. Okay, so Copilot is not helping. Um, I'm just going to not let Copilot do this. So choose delta by a tactic. Let's see if this gives me the, there we go. So sometimes you need to make better comments. Um, cool. So this step, actually, I probably should have said choose m greater than 0, choose m that is a real and is greater than 0, and introduces two hypotheses. This is probably a comment I should have done if I wanted Copilot to help us. Um, it's also good not to use Copilot so that you learn the syntax. But for today, I'm just want you to see how to do this in the most efficient way. And then you can like actively, like, do active learning from your head to do this so that you actually learn the language, you know? Um, cool. Okay, so we have this. Um, Okay, so we have this goal now. So at this point, Copilot's suggesting something. I don't think that's what I want to do. The reason is because right now this 0 is less than m minus 1 is like tacked on to this entire expression. Like it's basically, if you're this expression, it probably means some sort of like, so something like left and, like, and right, like like some sort of constructor, right? Right? It's a prop. So I can't really, like, Copilot suggesting something, but it's not really, yeah, you see, like it's suggesting this, but I can't do that on this gigantic and statement because like it's like trapped in this programming language construct called and, you know? So I want to take them out and separate them. So actually it suggested split. I wonder what that will do. Okay, it didn't do it. You could read the docs on why it doesn't work and read what the split tactic does. Instead, what I'm gonna do is okay, I'm just gonna tell instruct Copilot. So first I'm actually just gonna check if this is true by hovering on the and. Okay, okay, actually it didn't really tell me what the left and the right is, but by the way if you look how it like highlighted it, it tells me what the expression is. If it would have stopped before, say at m minus 1, before the forward arrow at the end, I would have known only that part is the input. But because I highlighted everything, I know what the left and right is. So my hypothesis was correct. In fact, I'm going to just keep hovering. Cool, I know all of that is part of the for all. Okay, this is part of the less than. Okay, cool. This one did actually tell me what the inputs were. 0, x minus 0, right? Left and right. And I'm ignoring the implicit arguments because it's not helping me. I don't need that right now. Cool. This one also tells me what left and right is. This one tells me what left and right is. Oh, it doesn't really tell me. It doesn't reveal the constructors. It's a little bit annoying. I would have liked to see the constructors of implications, whatever, but at least the highlighting and tells us what it is. So this type of the reason I'm showing you this, guys, is so that when you apply tactics, instead of like letting Copilot like randomly do things for you, you can tell Copilot, because Copilot remembers the syntax. So you can, by inspecting what your expression is, you can tell Copilot, okay, we have this. I want a tactic that does something like this. Does that sort of make sense why I'm showing you this? Besides it,
Yeah.
besides it being beautiful, like it's so cool. No, I don't know if you guys think this is cool.
Oh
Yeah.
yeah, it is. It is.
Wait, Brando,
Yeah, yeah.
what do you mean by seeing the highlighting?
Do you see in my screen that when I move from my cursor from places on the goal, I can see there's an and there.
Uh-huh.
And see how everything is blue?
Mm-hmm.
If I move it to the right, now something else is blue.
Oh.
What that's doing, it's saying and is a constructor
Mm-hmm.
propositions, and its argument, and that constructor encompasses everything in blue.
Mhm.
Oh.
Therefore, you can conclude 0 less than m 0 less than m minus 1 is on the
Mm-hmm.
left, and the remaining thing is on the right.
Oh.
Does that make sense?
Yeah, I think that does.
Yeah, so I can do that for every constructor. This one too. Now, because of the way it highlighted it, I know that 0 is on the left, x minus 0 is on the right.
Mm-hmm.
In this case, VS Code was nice enough to actually show me your function is called lt.lt, so less than. Actually, if I hover over it, it even gives me the definition with the implicit arguments. Okay, I'm just gonna ignore it because I don't care about that much depth right now. But these are all the implicit arguments, and these are the non-implicit arguments, right? They're like literally right there. Yeah, so inspecting things like this like gives you hints on many things. Like here, it'll give us a hint what tactic to use. to deconstruct. Maybe the tactic is called deconstruct, you know? If I were dealing with subtraction, okay, now I have a hint that the tactic in, sorry, the theorem that might need in MathLib is called sub. So when I ask Copilot or Google things, I'm going to use sub, not minus, you know, because I know that this is the type of words they use in the library. So this type of
Mhm.
inspection of the terms gives you hints on what the names of the theorems you might need, or just like what the term is, you know, because sometimes it's not clear. Maybe you don't remember how the parentheses organize. So like by hovering, it tells you how it organizes them, you know, what
Mhm.
belongs to what. Um, that is actually called, that's what we did with the infixes and stuff last time. Cool. It's called precedence. We can discuss precedence in more detail. Right now, you can just skip, like you can know where the parentheses are by hovering. That's the thing I want you to really remember. You can hover and look at what term belongs to who and what the name of the functions might be. The minus is called sub, and that might help us Google related theorems. Cool. Any questions? No? Eric, Emily, you still there?
Yes, no,
Yep, no
it makes
questions.
perfect sense.
Oh, okay. So what I'm gonna do is I'm just gonna try to deconstruct this and let's see if I can do it. So deconstruct, I'm just gonna leave that. Deconstruct to left and right. Um, I wonder if it's gonna do it better if I give this symbol. I don't know. So I'm just gonna left, right. Let's see if using a tactic. Okay, it did split, but we already did that. So I know split doesn't work. Come on, Copilot, try something else. Deconstructor. Does this work now? No, don't use. Okay, Scott also tried
Um,
it, but it didn't work.
does cases work?
I have no idea. Cases. I didn't like it.
Oh,
Oh, it didn't like it. Case. Does case do anything? Cases question. Does that do anything? Okay. This is not really helping me. Does apply work? Oh, cool. This actually worked. Yay, it worked. Okay, I cheated because you didn't know. You don't know how I knew apply would work. Do you want to know how I knew? I knew that we only have 2 minutes, but I think it's worth continuing until Emily, are you okay until 3?
Oh yeah, I should be able to go until 3, but I do have to head out
That
at around
that
3.
that way you really guys know everything and all the intuition.
Yeah, yeah.
Beginning.
I'm
hmm
perfectly fine with going until 3.
Yeah,
Yeah,
okay. So
me too.
before I tell you how I knew apply might work, I think honestly, I would have just Googled like different permutations of this into Google, and Google site search in the on and GPT-4. G I would have done something like that. That is one option. The quickest one is what I did here. So I'll tell you what I knew. So I'm gonna open up some notes from when I was at Illinois, I took like theorem proving classes. So like PL theorem proving classes. So I know a fact. I know how theorem proving works a little bit better. So let me tell you what I know. Um, what I know is, okay, this is the magic. Okay, let me show you what this is. So, um, all of Lean works by something called inference rules. So basically, when you define a logic system, like the ones you do proofs in, you basically outline all of the rules that are valid. So for example, calculus of constructions. Let's see, you can, I wonder if, okay, so these are all like the proof rules. What this means is that given any set of assumptions, the statement P is with type T is true. But it exists or is provable, actually, is provable. That's better. And what do you need to show that? Nothing. You can just basically invoke this fact randomly, basically. Okay, let me go to, yeah, these are a little complicated. I'm trying to find something simpler, like maybe natural deductions. Natural deductions. Maybe this is simpler. Proof system, maybe. Okay, something better came up. Natural deduction. Okay, this is a little bit more understandable, I feel. Let me just see if there's anything. Okay, cool. Okay. So you should check this article out, but I'll explain you the intuition. This is the intuition. If you have A and B, you want to prove that. There's our goal in lean. Um, you can prove this if you can prove A and B. You have proofs for both. That is the proof applied backwards. In forwards is like if you have A and B, you can construct this new proposition, right? It sounds obvious, right? I guess. Basically, if you have a proof rule and you tell lean to use the tactic apply, what it will try to do is match your goal with the proof rule and fill in the what A should be and B should be. So that is what I actually did. So I told lean, apply, do it to the goal. I assume the goal is the default. And it uses this in a dot intros is like this rule, actually. That's a funny thing that I chose the rule on the Wikipedia page. We can actually inspect it. Yeah, there it is. A implies B implies A and B. So that is the A implies B implies A and B is exactly this notation. A implies B implies A and B. Um, so I just told it use intros A and B and match it to our goal to deconstruct the constructor, and then we can prove the remaining things that you want me to prove so that the proof finishes. Does that make sense?
Yeah,
Yeah,
and
that
that's
makes sense.
Yeah, this is actually sort of important.
Yeah.
So
So whenever you have like a statement that's an and you need to prove it, you would apply and.intro and then prove both sides.
well, that is one way. If you that is
It's
one
one way to do it.
Yeah,
Okay.
I don't want to say that it always works. I just sort of the reason I knew how to do this yeah, because I knew this is our goal. And
Mhm.
actually, if you remember, this doesn't have it, but do you remember the previous one had gammas? Here, like now I'm gonna open calculus of constructions. There were gammas.
Mhm.
Those are just the assumptions.
Oh,
So it's saying if you have this is just the definition of what lean is. I think lean is calculus of constructions or some very similar. It says if you have this thing you want to prove, then you need to prove this and this. And then this goal will disappear, right? Because now you only need to do these left and right.
yeah.
Yeah, so that is yeah, and sometimes the proof rules will like introduce things into the environment. Yeah. Um, that makes sense. This is like it looks like the intros rule, right? We have for all A, B, um, introduce X of type A, and for all A, B is like the object. So now, yeah, I don't know, it sort of looks sensible to me. Um, cool. And let's see. I was gonna say one last thing. The process by which lean matches the constructor contents to the rule is called unification. So unification, now you're getting like all my knowledge of like um PL, Wikipedia in a 2 hour session. This is like a lot of learning. But like, okay, unification is like pretty important for formal methods. So what it's actually sort of simple. You intuitively know what it did, right? It has a rule. It's arrow, arrow, A and B, and it matches those symbols to like our goal. Our goal is this. So basically it tries to match the thing on the right of intros, right? This A and B. And once it matches them, that's that's a process is called unification. Once it uses the unification algorithm, it tells you what A and B is and updates the rest of the environment for us. So unification in a simpler setting is actually just simultaneous equations for symbols, I guess. That's the way I think about it. It's solving equations. So if you have const is just some sort of constructor. If you have const x, nil is like an actual value, const 2, y. This is just some sort of like set of symbols. If you want to unify it with, let's see, what is it? Is a syntactic first order unification? Okay, so this is trying to, we're just saying, we want to solve this equation. Tell me what x and y need to be so that this it makes sense. So I guess, obviously, you see that 2 should be x and the y should be this. And now, because we know what x is, we plug in 2 here, and that is what the solution is. That is what the unification algorithm should return every time. Um, yeah, that's it. Basically. Um, yeah, you can skim these pages to get intuitions on what these things are. Cool. Anyway, let's move on. We're gonna tell it focus on the first goal. Okay, so now we remove the other one from our local environment on the right. And um what I think does that work? Okay.
Wait,
Sometimes
that's what the dot's doing, right? Sorry, that's the dot is like you look at the first goal. It's kind
right,
of like canceling.
right.
Okay, okay.
Yeah.
Thank you.
In Coq, I think it's minus and then you do it. Does that work here too? I don't know if it does. I, um I don't know if it I guess
It
it
looks like it made the two goals only one, so it only shows the first goal now.
yeah.
Yeah.
I guess it does, but then it didn't put the right thing. Anyway, I was just curious if the syntax from Coq worked. This is the correct syntax here. So exact is it actually just finds the exact proof statement. It happened to work. Interesting. Oh, actually, it should be obvious to us, right? Is it? Should it be? We don't have
Yeah.
it shouldn't, no, it's not in the environment. So it's not an assumption. So you do need some sort of like lemma. Um, HM pos. Okay, I see it. Okay, simp does, I guess simp finds enough simplification rules for us. Um, I think this is good for now because the proof is so simple. So what we could try is to do it manually. Um, yeah, I think I'm gonna leave it like this for now. Just for to save time to make sure we do the rest of the proof. But to do, maybe we have time to come back is try to find the lemma. Just so that we can get that skill, right? To find the lemma in MATLAB to apply to prove this. But I think we're gonna do that anyway in the next proof, so I'm just gonna skip it. But that Copilot worked. Thank you, Copilot. The lemma is simple enough that it maybe shouldn't be too surprising that it should work. In fact, simp does simplifications, and it maybe should be obvious that since HM pos is like H is positive, then maybe that makes sense that that lemma should work. And in fact, I'm glad I clicked. We can actually see how it progresses. Okay, look, it made it. I had applied some lemma um to make m minus 1 m, and then it closes everything. So it used our fact, and then it closed our goal. I don't think it works without this. Yeah, right? That makes sense, right? Because it doesn't know anything about m, right? It's just m. This is not like generally true, right?
Yeah, I see.
Like if m is 0, it's not true. But m is strictly greater than 0, so it needs our so simp needs our hypothesis, so that if you know modus ponens, like modus ponens is something like A implies B, and if you have A, you can conclude B, right? It needed our hypothesis so that when simp found the lemma for us automatically, whatever the lemma was. The lemma is probably something like 0. This is the lemma. Implies 0. This is the lemma. Like literally the fact we need. I'm just guessing how I did it. And A is this, right?
Yeah.
Actually, it didn't even do like it knew to simp did modus ponens for us. It just found this lemma in the library and then it just applied it via simp and our fact. It gave it our fact. Cool. Anyway, let's move on. Okay, so what do we have? We have all of this. Okay, what is the first thing you guys would do? Now you guys have seen me program a little bit in Lean, so maybe you have a guess.
I guess intro X
Yes,
to get it out of the for all.
right. And look, there's more things on the left. So I would probably try to introduce those two. So intro X. Cool, okay. Okay, now we have this goal.
We can apply the and thing again.
I think we can, but apply, so we need to, okay. So
Oh,
I don't
Could you
think
actually
wait.
apply it?
I don't think apply will help
And-
us, but I'm gonna try anyway. Okay, yeah, it doesn't let us do it.
Okay.
Oh.
Because apply applies to the goal, but the goal is an implication, not it's not only this, right? Like the left, so think about it this way. The left-hand side is an assumption we get for free. So apply, I don't know if there's an apply function that will do that. Maybe apply, no, because apply will try to, oh yeah, apply would probably work if we find the right rule, like proof rule, because it will figure out that if there's probably some proven, like some proof statement, some proof judgment. I don't know how they call these. I forgot the lingo. Inference rules. There's probably some inference rule that says if you have an implication and you have things on the left, put them at put them in the environment, right? If you remember, there are rules that modify the environment. So that's probably there's something like that probably somewhere. So maybe we can do that. Um, oh, it didn't no goals. Um, okay. Okay. Yeah, it cares about the tabbing, like the spaces. That's why it didn't show me the proof until I pressed tab. Okay, I'm gonna make a comment and let's see. Um apply implication tactic so we can introduce the assumptions into the context. Oh, that didn't quite do what I wanted, but I mean, okay, fine. Deconstruct the okay, so this did work, right? Do you see that, guys? It did move it to the assumptions, but we have this horrible and statement.
Yeah.
Let's see if we
Oh
can.
wait, so intro is the thing that modifies your environment.
Yes.
Okay. And then if you so you can just name like whatever you want to name your hypothesis, and that takes your entire like the left side of your imply statement and puts it into the environment and changes your goal to the right side of the implies.
Yes,
Okay.
I can actually put it there and it does it in one goal, in one step. This is probably, yeah. The reason I knew that when you said intro X, but I knew the reason I didn't do that is because I was trying to see if I could only introduce X and then have a different tactic that introduced X and broke the end at once. Like in the next step, I wanted to break the end, like break the end and introduce it to the environment. Instead, it introduced the end into the environment. So I'm not gonna let it do that. Let me try to see if I can get it to tell me what the tactic should be. Apply implication tactics so that we introduce the assumption into the context by separating, maybe deconstructing the and statement. Let's see if this works. Okay, it again didn't do it. Does intro question mark do anything? I have no idea what that does. Sometimes that works. No. Okay. Okay, so it didn't work, so I'm just gonna let it. Fine. I'm just gonna let it do whatever it wants and just gonna say deconstruct the and here. I wonder if it can I wonder how if we can tell apply it to the environment. So it's with a tactic. Okay, it's now trying to do crazy stuff. No, that's not what I want. Um, does apply have like a backward? Um, oh, sorry. A backward way to apply it? Oh,
Wait, what if we do like exact by simp something? Because the assumption that x is greater than 0 is in the uh or I guess x is smaller than m inverse is in the hypothesis here.
yeah.
And it's part of the and, so you know that it must be true because it's part of the and. So could Lean use the exact statement to just prove it from that?
Um, well, what I want to do is break this out, simplify the -0, and then invert things using all of these steps that we have here. Like actually, I'm trying to write this proof over here that we wrote by hand.
Okay.
Yeah, so we
So
would still need to break apart the and
yeah,
statement.
I don't know how to I don't know how to do anything without breaking apart the and. Um, yeah. So in the we can come back to trying more things. I'm gonna comment this out. Oh, it didn't let me comment it out. I'm gonna comment this out and I'm gonna instead cheat and know some magic syntax in Lean that it didn't. I mean, I think at this point other options are the usual ones, which are putting this in Google, GPT-4, asking someone in Zulip, asking someone in Lean Prover Club at Stanford. I don't know if I forgot any other ones. The Proof Stack Exchange, just basically Moogle, just trying things. But I think I even tried the exact question mark. At some point, knowing more Lean helps, and I'm gonna use that fact. I know that intro X has this way to um just do what I'm trying to do in one step. So this, yeah, it did it. Now it did what I wanted. So what it did is that it did the intro, but it introduced stuff using the constructor. And these Langle Wrangle um tells Lean how to deconstruct it, basically. This is what I learned from
Even
Scott on Thursday, basically.
it wasn't just like a normal parentheses, right? It was like a slash lang.
Yeah, I did
Oh,
angle.
Oh yeah,
oh,
it's
okay.
kind of hard to see on the video, but if you zoom in, it's like pointy instead of round.
Oh, okay.
Wrangle.
Okay.
Yeah. So that is like the general. So I can zoom in a little more, but then we won't see our proof very well at the top. I want, yeah. I'm gonna, yeah. Um, yeah, so I did that because I knew that. I wonder if intros. Okay, at H. I'm trying to see there's like some sort of thing that would suggest me that there's more features to this tactic. I can't see it just by looking at this. Um, yeah. I wonder if like let's see, intro XY, intro, yeah, it doesn't really say anything. Yeah. For now, I'll just take that I know this for now. Cool, and let's just move on because we have 10 minutes to finish the proof. Um, let's see. Okay, let's just remove all the minuses. Um, what I would try to do is, oh, um, rewrite x minus 0 to x using a tactic. Okay, let's see if that works. Okay, sub 0. We already knew sub would be the right thing, right? I forget how we knew, but we inspected something previously, right? Actually, we inspected the symbol we want to simplify. So let's look at the symbol we want to simplify. Sub, that's maybe like gives us a hint of what type, instead using a tactic or subtraction. Maybe this gives for sub, this increases the chances that Copilot gives something sensible. Oh, what? It didn't like it. Okay, this is not good. This is not correct syntax. Okay, now it did it. Woo! Actually, let's just do the other one all at once. Why don't we do both? Yay! We did both. And um x minus 0, or what was the other one? It was um x plus. Oh,
I think both of them are
oh
x minus
yeah,
zeros,
and
but
they're both.
with different.
Yeah, they are. Sorry, I just sort of got confused for a second. Cool, that worked. Okay, now we have the statements that we want. Great. So now we want to formalize, we want to do basically, we've arrived here in our proof, right? So this is more or less what we want. Okay, let's put it on the top, on the bottom right here, so that we can look at our proof. So the first thing that we want to do is that we wrote here was we want to show this. Okay, we want to do this. We want to multiply both sides by x minus 1. So let's do this. Okay, using a tactic. Oh, okay. That introduces, okay, yes, we do need that lemma, right? Right? Do we agree we need that lemma?
Mm-hmm.
We need that,
Yeah. Yes.
Wait, is that?
we need that lemma if we want to multiply x minus 1 on
Both
both
sides.
sides. So that,
Oh, okay. Yeah.
yeah. Okay. Okay. Does that work? Okay, that doesn't work. Okay. Okay. I wonder if this will do something. Okay, yes, this does. Okay, cool. Okay, rewrite question mark suggested a bunch of things. Um, so actually I think this closes the goal, the entire proof. Oh no, it doesn't. Oh, what did it do? Sorry, I'm just sort of now playing with Lean a little bit. It didn't. Okay, anyway, I just wanted to show you that feature. You can play with it when you have more time. Our W question mark. What I liked is that it actually shows me mult left. So multiply less than left. That's pretty much what we want, right? We want to multiply just by the name of the theorem. You see that what Copilot's suggesting? I'm just gonna let it do it. I know the question mark shouldn't be there. Oh, it didn't let me, it didn't, something didn't work, but it gave me the name of something that looks useful. Um, okay, look, this is what we want. Okay, can we do like print? Print. So I'm just putting it there so I can see it. We're trying to multiply both sides by a. Okay, that is an implication, right? And if and only if. If a is less than a, then we get this modus ponens on both directions. So let's do that. So let's just ignore whatever Copilot said here because it's sort of not useful. What is this? Okay. So would this work? This looks like the right thing to do. Yeah, okay, so let's see. We have, oh, we have we have, we just want to multiply x minus 1 on both sides. X minus 1. No, we want to multiply. So our proof, what did our proof do? Sorry. X minus 1. At this point, we have m is less than x minus 1. I see. I think what I would do, sorry, I'm just looking at the proof now. I think what we want to do is manipulate the goal so that it matches this, so that we can just say the assumption is on in our hypothesis, close the proof. So I think actually the right thing to do is multiply by x, the goal, and then multiply the goal by, and then the identity, and multiply the goal by m minus 1, and that should close the goal. So let's do that instead. Okay, I think that lemma is still useful. So let's do multiply both sides by x. We already have x's. Okay, we already know that the hypothesis holds, right? Via multiply both sides by x. We know 0 is greater than x, so it should work. Use a tactic. I think it's just a rewrite. We don't need this anymore. Oh, maybe would that work? No. Okay, hold on. Cool. Let me see. So we want to multiply both sides by x. So we want to multiply the goal. And this proof, this lemma is this. So the lemma that we have is this. So A, okay. Okay, so we want this direction. So we want this direction. I wonder if that will work. X is positive, maybe? Yeah, okay, it did it. Did you see that, guys?
Yes.
Yeah. Wait, how did you
Yeah.
do that?
I okay, so I just copy pasted the name of the hypothesis.
Hmm.
I copy pasted the name of the hypothesis. Then, so I realized I needed this assumption, right? For this to hold. That is what implicate like you can think of function types as arrows, so as
Hmm.
implications. I knew this was like left-hand side of an implication. We have that in our hypothesis because x is greater than 0. So
Hmm.
I told it but it has the lemma in reverse. Like it has the lemma, like, it wrote the lemma in reverse from what I needed. So
Oh.
I just told it apply the lemma in reverse.
Oh, so the
Rewrite-
way the mul left than mul left thing
uh,
works is like if A times B is less than A times C, that implies B is less than C, but you want,
yes,
okay,
right.
I see.
So I sort of used it in reverse. Actually, I think I could have done this. Um, modus ponens reverse. Ah, okay, darn, this didn't work. Sometimes that works. I don't know why it didn't work.
The arrow, the left arrow, like reverses the statement basically, right?
Yes, this left arrow
Okay.
applies the statement in reverse, but I was trying
Okay.
to just get the reverse statement by doing dot modus ponens reverse like this. There's like some notation like this that works sometimes in lean. I don't know why it's not working right now, and because we're running out of time, I don't know if I have time to figure it out. But hx positive, we needed this. Without this, like it did it gave us this really, it did what I wanted, but it didn't multiply by it like, it produced some random automatically defined number, right?
Mhm.
Like that's not what we want. So I told it which number, like I used this, it used unification to figure out that it wanted us to do X.
Mhm.
So now I'm gonna see, my
Yes.
intuition tells me that simp should work. No, it doesn't. Okay. Something
Do you
should,
have to rewrite it again using, or first do the identity,
right, but
multiplicative identity?
right. I'm just trying to figure out how to get the identity. So rewrite using a tactic and the identity. Oh no, the identity. Okay, yes, that's true. Okay, did it work? Okay, no. What is this inf mol cancel? I think this is what we want. Oh darn, but it says x is not, then we have to show that x is not equal to 0. Oh darn it. That is complicates it. Hmm. Okay. Um I wonder, I'm gonna keep
Don't we
trying.
have that with xh pos that it's greater than 0? Does that imply that it's
Yes, we need to use x is greater than 0 to show that x is not 0, and then
Oh, okay, okay.
that's
Oh, okay.
the issue.
That
Um,
is
Mm.
so I'm just trying to figure out some different. I'm just trying. Being a little random right now, just because of the lack of time. Um, okay. None of these things are really helping. I'm gonna remove this. I don't think we need this anymore. Let's see. Exact question mark. Does this help?
Oh,
Goodness.
wait.
Does this close the goal? Oh, my computer's running out of battery. So I'm gonna connect it real quick. Um, okay, this didn't do anything. Okay, let's try something else. Let's try simp question mark. Okay, simplify using a tactic and the identity theorem. Okay, I wonder if this will give us better suggestions in Copilot. Okay, that didn't. Yes, it does want H inverse. I think this is fine. We need this. And this is, yeah, that is the right thing. Yeah, this is right. I feel like this should be easy to calculate. I don't know why it wasn't easy. Um, okay. So we want to rewrite to the right, from left to right, so we don't have to do the inverse arrow. And it needs H. Okay, have H. So H is X not 0, right?
Mm.
Oh, it didn't like it by that. By sorry. I'll just pretend it's true. So sorry is just a way to, but I just want to see if that theorem works. Okay, but why doesn't it work now?
Do you need
H,
a left arrow?
I don't think so. Let's see, we have this theorem. What proof state do we have? I'm gonna copy it because I keep forgetting it. We have, this is our proof state. Um, oh, it's not the actual thing we want. Um, so I wonder if we have to show that they are equivalent. That would be a little bit annoying. Um, hmm, have H equals by sorry equals 1. I wonder, do we have this hypothesis now? I just sort of want to know if we can do this now by H. It didn't rewrite it. Yeah, I don't know why. Cool. Um, Darn. I know that it's 3:05. So should we continue this proof later?
Sure.
Yeah,
So
we could. I gotta head out because I have to be
yeah,
somewhere at 3:15.
the good thing is that I do have a different proof that worked. This wasn't the one I tried at home. Um, it basically solves everything at once here. We can
Mhm.
figure, we can look at that proof later and it worked.
What
Uh,
is our like rewrite and then A? What does the A mean?
the A means, I didn't know what it meant either. What it means is that it closes any goals that are obviously that are in the hypothesis. So
Oh,
if you have the hypothesis
uh-huh.
and the goal be the same, it means your proof
Mhm.
is done, right?
I
Yeah.
see.
So that's what RA does. So let's see. We can just copy this here and see. This is a very good attempt. I think we were very close. Um, this should, okay. This, oh, unfold F. Okay, we already unfolded F. Oh, I don't think I defined it like this. M is positive. Yeah, M is less than or, yeah, I define. There we go. We did it, I think. Is it? Yeah, I think
Yay.
we did it.
Also, I'm really sorry, but I have to head
No,
out.
no
Like,
worries. Um, awesome, guys. So cool
yes.
session. Let's continue later.
Yeah.
All right. See both of you.
Okay.
I'll see you
Yeah.
on Friday, right?
Yes.
Yes. Okay.
Mhm.
Bye-bye.
All right.
Thank
Bye,
you.
Emily.
Bye-bye.
Bye.
Okay.
So let's finish the proof. So the last thing we did was this subtraction, simplifying the subtraction. So before I do that, I just want to recall or actually mention the mathematical motivation. So the goal has m is less than x minus 1. So by simplifying the subtraction minus 0, like the minus 0, we get it in the form of the goal, basically. And this is in contrast to limit proofs, standard limit proofs. So standard limit proofs have um, a 0 is less than or equal to x minus c, is less than delta, implies 0 is greater than some function value minus L, the limit point. So in this case, because the standard, or the more traditional or more intuitive technique to solve this might be to quote unquote find the inverses of F, and then you get X minus L, and then that inverse applies to L, then L and C might be the same. And if that's true, then F inverse is delta. That's like one way to think about it. The main point is that usually the right-hand side has to be put onto the left-hand side to prove this implication, um, basically, or just having match so that you can close the goals. Yeah, in this case, the goals are not of that form, so we can just remove the zeros, i.e. the minus C. Anyway, um, now that we have that, so let's see. Um, Okay, so we have this, and what we want to do, if we recall, let's see if we have space for it. If we recall our pen and paper proof, maybe it can help us. Oh, I don't know what happened to, okay, pen and paper proof. Um, we are we are at the point where we want these to match. So we know that we can just, one way to do it is to actually, let's manipulate the goal. So let's multiply both sides by x, and then both sides by m minus 1. Apply the identity whenever, the multiplicative identity whenever is possible, and that should finish it. So let's try that. So first, so multiply um, on the right by x. Let's see if it, have no. Multiply, rewrite. So rewrite, let's try that. Uh-huh. Why is it doing that? No, that's not a good suggestion. Um, let's see. So multiply. So yeah, let's see. Multiply using rewrite tactic. Let's see if this helps. Just I don't think this is what I want. Okay, so that's not really helping. So, let's think about it. So what can we do? We have, let's see our goal again. Um, so maybe we write it as an equation. Multiply by right. So let's see, maybe let's do um let's have m times x is less than x to the minus 1 times x. M is less than x. So let's just basically write what we want and see, okay, and see we can get rewrite to give us a good suggestion. So rewrite, using rewrite to I multiply, um, is it on the right or on the left? Oh, okay. There is a typo. Using rewrite do. This should be a 2. Yeah, by multiply, playing both sides by x. Yes, that is what I want. On the right. So rewrite. Okay, this was close. Okay, this changed the wrong thing, but at least it gave us the name of the hypothesis that we want, and it's giving us the left one. So in this file, right below, we have the right one. So I'm just going to copy the main part of the theorem that we need. If we see this is theorem, the name of actually, let's just get the name, molt less than mol right. And this helps us get used to how mathlib defines things. So we can tell it print it, or actually just, I think I can just hover over it. And this is what we want. So let's just remove it. Maybe we can just comment. This can be a comment. And this part, since we know that intros are putting hypotheses into the space, then we know that this is actually we need a is less than 0 for this to hold. So let's see, we're multiplying by x, right? So if we multiply by x, let's see, can it show us our goal, original goal? It doesn't want to show us our original goal, so I'm just gonna, okay, here. Okay, yes, x is less than 0. 0 is less than x, so we can use that. So x is positive, so we don't need the reverse, I think. Okay, the theorem is, yes, we do need the reverse. Oh, I don't know why it doesn't let me see the goal. I think the print statement confuses lean 4. So, okay, so we have that. We want to multiply x on the right. So so we want to go from right to left. So this is correct. So I think this is what I want. H left. We wanted to apply to the goal. So maybe this is what we want. It is it multiple oh we still need this arrow. Oh, the other arrow, sorry. Yay, we got what we wanted. Now we use the identity. to cancel. So maybe it's like multiplicative identity or canceling. So using rewrite, let's cancel the x's, i.e. x equals 1, or use the multiplicative identity lemma. So let's see. Maybe I'm writing too much and it'll confuse Copilot, but it's worth trying. Okay, did that work? What is this lemma? This lemma says a times, okay, if a is not equal to 0, then a times a minus 1 is 1, which is what we want. Okay, we need to flip it, so we need to do commutativity first. So let's rewrite and try mul commutativity. Just do that. Great. Now we need, if we remember, this lemma required that we had a is not equal to, it required this fact. So let's define a lemma for a is not equal to 0. So in this case, it's x, using the fact that it's greater than 0, and see if Lean can help us. X not equal to 0. Yes. Okay. Okay, it gave it right away. So that's useful. So it just says if, okay, that is exactly the fact we have. If b is less than a, i.e. if 0 is less than x, then a is not equal to b, i.e. X is not equal to if 0 is less than x, then x is not equal to 0, which is exactly what we needed. Cool. It defined it. For us, I'm surprised it just did it. Maybe it's why. I'm just sort of curious now. Okay, it takes in h. Okay, it takes in that fact and returns that type. Okay, that's why. So it takes another way to view these are as functions, right? So the function has type b is less than a, and that is what this type is, and it gives us a type a is not equal to b, and that is what we got. Okay, cool. Yay, that was sort of simple. Just, I didn't even need to use exact. Surprising. Okay, cool. So we have the fact that we want. Can we just plug it in? We cannot plug it in. Why can't we plug it in? Mul is x fail did not find an instance pattern x inverse times x. So what is the name of this? Okay, it's wrong. Okay, so we don't need to do this, I think. A times A inverse. Oh no. Oh, we do need to do it. It's x in, okay, in the goal it's x in, what's confusing? Oh, it applied it to the wrong thing. Yes, I guess it applies it to the first thing in the goal. So how do you apply it? Okay, so apply commutativity to the end part of the equation. No, I don't think this will do what I want. I wonder if there's some sort of like goal dot two, because the goal receives two things, and I wonder if I can like just refer to that. Rewrite at I wonder if this makes any sense. To goal part 2. Does this do anything? I don't know how to refer to the goal. So let's see. Referring, doing a rewrite. Okay, maybe we can just look at the docs for rewrite. Rewrite, but also tries raffle, that's fine. This is just rewrite, jump to it. Okay, it doesn't really, that wasn't helpful. Okay, rewrite, clean documentation. Mm, what is this? Yeah, so this is what I'm looking for. Okay, rewrite. This is what I wanted. Not very useful. I was hoping it would tell me more details about rewrite. Okay, I wonder if there is a way to do this somehow. Rewrite on the, okay, how do I specify rewrite mean a specific side of the goal? How can I apply a rewrite to only one term? This is lean, because this is what I want. Okay, rewrite writes all identical terms simultaneously. There is a different tactic nth rewrite, which only rewrites a specific occurrence of a term. You need mathlib for nth rewrite, and I'm not sure it's available in natural numbers game. Okay, that's not what I don't care about natural numbers game. Um, from the writing, I wonder if this is lean 3. It looks like lean 3. Okay, nth rewrite. I wonder if question mark does something. Well, I already knew that this would actually do something, but that's not what I want. Um, and rewrite to. Okay, it did it. Yay, thank you, Stack Overflow. Let's reward these guys. Cool. Okay. Okay, it's now in the format that we want it. Right, we even copied the equation that we have. It's this one. Cool. So let's just keep going and rewrite. Cool. It requires mathlib, so that's why it worked. Now that we have n is not equal to 0, it should work. Yes, it worked. So now let's basically do the same thing now. Let's multiply on the left by m inverse and have the equivalent theorems. So using using tactics, so let's multiply both sides by m inverse and inverse. Okay. Then we can use the fact that then cancel the m's, then simplify m equals, and then then simplify m times 1 equals m, and then that is the goal, and that then close proof. Or then discharge the final proof. Whatever. Cool. Okay, so let's do that. So now we are multiplying both sides on the left. Let's do left. And for that, we already know, okay, so this is the statement. So let's try to do a rewrite. And we're gonna use some, it's probably gonna be the same. So we're probably gonna need to use the left one arrow. Yeah. So we're gonna need the left arrow, and we're gonna use mul less than or equal mul right. And for that to happen, we're gonna need that h is positive. Perfect. That did what? Oh, that's not what I wanted. We want to multiply by m inverse. So we need to state first that hm inverse is positive. Great, this worked. The proof was a little bit more complicated than I thought it would be, but it should be just basically, where's the other half? This one, hm pos. I wonder if we can just do it the same proof. So this one is, oh, no, that's not the same proof. Yeah, those won't work. Cool. Okay, so this makes sense. So simp knew to use this fact that h is positive to conclude that m inverse is not positive. Actually, there is a theorem for this. I remember seeing it somewhere, but I will leave it like that for now because this already worked. So, okay, hold on. So multiply m inverse. Okay, it didn't work because this still has the wrong thing on the left. It should have been on the left. So I thought I used left. Maybe Copilot did it. Oh no, why is the associativity weird? Well, okay, let's undo that. Rewrite. Okay, that's fine. Um, what is this? I was just sort of curious sometimes what Copilot suggests, but what I want is yeah, the suggestions on the right look not exactly what I want really. So I just want to change the associativity. So rewrite. Okay, so rewrite m star m inverse times m times x via associativity. I think it's associativity of multiplication. I don't know why it also said commutativity. It doesn't know what it's talking about. Okay. Okay. Okay, maybe because there's three things going on. I'm not sure why. Let's see. If we have all of these things, let's just write it down. If we have A, B, C, or okay, it's just probably this then. Yes, it did it. Great. We're progressing. Now we do need to do the canceling. Uh, cancel. Cancel the m's. Cancel the m's, right? That's what we need. I think that should work. Okay, that doesn't work because of the not equal to 0. Yay, okay. We have m is not equal to 0. Yes, this should work. Great. Okay. Why didn't this work now? Or- or- Okay, hold on. We have M inverse. So M is not equal to 0, but what we need is M inverse is not equal to 0, I think. I'm not sure right now. Let's see, just look at it more carefully. Here we have M inverse times M times X. So we want to have M inverse times M equals 1. X, in what form is this multi-cancel thing? It's A times A inverse, so we need to apply commutativity, I think. I think that's what we need to do that. Commutativity. Oh, did I do something wrong? Mulcom. Okay. It didn't apply to what I wanted it to apply because of how the star is binding things. You can probably inspect it with this. Yeah, that's not what I wanted. Okay. Hold on. Let's just take a step back. We have all of this. Only thing we need is M inverse times M to be equal to 1. Okay. So for that we need this theorem. We need this theorem. We need the cancellation inverse theorem. So for this, that's equal to 1. But now we have, yeah, when I tried to do, so we probably have to do nth commutativity again of the first thing. No, that's not what I wanted. Oh, does simp do anything? Okay, I don't know. Okay, cool. Simp did it. Cool. Okay, based on nice. I didn't needed to do it manually because of the theorems I've been collecting. It applied all the manual manipulations I was trying to do by hand, I suppose. Um, cool. Then we have this, and that should be the assumption. So that should finish the proof. Woo, we did it. Huh. That ended up being very different from my other attempt before this one. So what I wonder what I did differently. I'm gonna close the proof viewer real quick, or I'm gonna just have them side by side. Gonna make this smaller. We don't need the entire thing. Just looking at the proofs side by side. What did I do differently? So I did some choice differently here. After I simplified, we multiplied by the right first. Um, Actually, the new proof ended up being longer. Yeah, it felt longer. I wonder why this is not highlighting it. Oh, it's wrong, I guess. Is there a mistake here? I wonder if there's a mistake on the other one. One goal. Okay, yeah, there's only one goal. There's only one goal. And that goal is okay, I don't know why it's not highlighting things. Confusing. But yeah, the main thing that changed was Yeah, the different, we first did the multiplication by x, right? And in this one, what did we do? Then we did the multiplication by x inverse. Did we? Let's see. On the left, we did multiply by x. And in this one, we multiplied by x on the right, multiplied by x on the right, multiplied by x on the left. Okay, I don't know. Seemed at some point it made a difference. Cool. Thanks for joining me. Okay, one more time. So last time I finished, oh, what's going on with this? I finished the proof with simp here, and I just finished the proof, I think. Okay, let's just uncomment all this. Yeah, it just would, yeah, and the main thing is that we had the m minus, I think without this it wouldn't work. Yeah, okay, it doesn't even exist. Without the x is not equal to 0, so it doesn't know how to do it. Simp. So it really does require us to know that we needed the fact that when m is not equal to 0, then we need that for the cancellation. Okay, so for that, how did I do it? Yeah, that simp does need it, and it finishes the proof. But instead of doing that, let's try to do it by hand. So we know that we want to, that mole cancel does this, right? Okay, it's not quite in the right form that we want it. So let's do again the nth rewrite by telling it which rewrite to, in which order to do. For some reason, this one does the wrong one. Yes, it's because it finds the first instance of multiplication, but this one is the second, right? The one inside the other multiplication. So let's go back. There's this one, and then there's this one. So this one's, if you imagine this as a syntax tree, and this star is at the top, x is on the right, and there's another multiplication, and m inverse is on the left and m is on the right. That is implied by the highlighting. So this highlighting is blue, this highlighting is blue. Cool. So this highlighting is blue, and this highlighting, that's how we can know because of the highlighting. This highlights everything. So it's at the top of the tree, and this one's on the left. Cool. A little annoying that it opens the bubble like that. We remove this bubble. Okay. So therefore, what do we want to do? We want to multiply, we want to cancel that inverse, and we already know that it requires this assumption, right? Remember this theorems have types, and this is the arrow type on the left. We can move it on the right, and it really means an arrow, implication. So, but we're in dependent type theory, so that is we're in lean, better said, probably more precise. So now we want to multiply, have 1 times x be x. So if you just do it, it doesn't work, because if you look at mole 1, it's a times 1 equals a. And that's not quite that doesn't unify with 1 times x, right? The 1 is on the right, our goal has it on the left. So let's flip it, because it's real numbers, so commutativity works, it's a field. Great. Let's simplify it, and then we finish the proof, because the goal is in our assumptions. This is exactly what we want to show, right? And we have it. Yay! So we finished. So now the proof is done. Basically, x has to be less than n minus 1. And we already have that x is greater than 0. Interesting. Now looking at this proof, it doesn't quite look like arriving at the exact goal that we had here. Yeah, I wonder at what point in the proof process this changed. Yeah, probably if we would have followed our pen by paper proof, it would have been better. Cool. I wonder if we should just try it since we're already on a streak. Yeah, why don't we try it? Let's just create yet another proof of this. We have lots of proofs of this now. At one point that we diverge. So at this point, okay, it is, okay, we diverge. Okay, so we have m is greater than x minus 1. So we were doing the proof from the back. We were doing like backwards reasoning. That's why, because we were manipulating the goal. If we would have manipulated the assumption and had it match the goal, then it would have been probably how we wrote the proof by the pen and paper proof. So why don't we try that? It's not too hard. It's manipulating this. So we need to multiply this guy by m on the right. Then we cancel m. Then we multiply x inverse on the right. And we write that all in lean and they would match it. So the rewrites would probably be at this, at hx less than or equal. Why don't we try that? So rewrite. Oh, cool. It did do what I want. Perfect. And I'm gonna do it a little bit. No, not quite. It did the wrong one. We wanted m pause. Yeah, now it's the one we want. I can't remember. So let's see our previous proof and see in what way is how is multiplication the identity defined. So mul this one. So I think this is the one we want. So print this. Oh, sorry, I forgot to write print. Print it. Yeah. So this is what we want. Let's make it explicit so that we can all see. This is what we have using this, using multiplication inverse cancel. So let's just cancel that. So redo rewrite. Mul cancel that. Yeah, that should work if we had the right, if we knew this is true and if we flipped it, right? So let's flip it. Let's just try to do rewrite. Mul com. I wonder, does this work? Mul com? No, why not? So we are going to look at our previous proof just to make it quicker. What the lemmas that we need or the theorems that we need from MATLib. Com. I guess that's not this one. This one is probably better. Let's put it here. Com. Mulp-com. Okay, mulp-com is AB equals BA. We need to say it at HL, and it multiplied the first one, but we wanted the second one. So I wonder if nth rewrite will do it. Rewrite 2, rewrite 1, rewrite 2. Okay, cool. It rewrote the one I want. Now apply the lemma. but now it says that we need to prove that h is not equal to 0. That m is not equal to 0. M inverse is not equal to 0. So we're going to define m pos, unless we had it already. We don't have m. Oh, m is not equal to 0. That's the theorem we need. It's not equal to the lemma, I guess. Is not equal to 0. And we need to do it with m. Cool. We got it. Now, this should work, I think. Unless the directions aren't working or something. Okay. Cool. Yeah, that's what we have. Hold on. We have this. Let's remove this. And then here we have, yes, then we need, yes, this is what we want. Great. What is this complaining? Application type mismatch. A times A inverse. But it did simplify it. So that is at XL. It's because it's not simplifying the right thing. No, yeah, it is. X is less than M. That is the right thing. I don't quite understand. Yeah, right. Okay. Okay, it's because this is not the, it's because we're trusting Copilot. Okay, yeah, then this won't be right. Yeah, that it's just the way we did it previously, but it didn't work this time. So we're trying to say M is not equal to 0. Okay, great. Yeah, it cares about the orders because of how things are defined. So we just need everything to match exactly what math lib has. Okay, so now we have it. Okay, great. Now we just need to multiply x inverse on the right, both sides. And that should complete the proof. Multiply x both sides by x inverse. And simplify. I wonder if that will work. Yes, that is the right thing to be simplifying. Yeah, of course that's not gonna work. It has to be on the multiply both sides by x inverse on the left. Okay. Left, and it requires that inequality. Yeah, okay. Don't do that. X is positive. I think that should have worked. That is the right statement. Okay, it's the arrow. Great, it worked. Okay. X should have been multiply both sides by x inverse. So we needed to have x hx inv is positive. Yes, and it's using, oh, cool. Inv of, it's using the exact, cool. I was looking for this fact that if you have the inverse, then you have, if the inverse is positive, then that value is positive. And MPR is the notation for modus ponens right. think if you use 2, it should have worked. Reverse modus ponens. I think this should have also worked, and it does. Oh, sorry. Modus ponens, right. Reverse, sorry. Cool. Okay. So that is so that the multiplication works. We need to plug this in here. Yes. Okay, now we multiply correctly. Great. So now we need to apply associativity. Apply associativity of multiplications to the of mole. Let's see if that works. It did not like it. Okay, mole. Okay, maybe it's just the left arrow. Yeah. Okay, now it has it. Now let's see if we can apply to the first term and rewrite. We're just trying to do, this is the second depth, so we know it's 2, and we're just trying, is this in the right form for inverses? It's not, because look, we have it here, so we are gonna do this. I wonder if we can just plug it in here and then do it. Okay, fine. Can we then rewrite? Can we do the rewrite for, it's not letting me do it. Okay, hold on. What? Okay, so we just want to cancel the x's, right? So for that, we just need to apply, we need to make sure it's in the same format as this. So that's what we want. We want this. So yes, flip it. Great. Okay, so now we need to cancel the x times x inverse to 1. Okay. It needs x is not equal to x inverse is not equal to 0, so we probably have to define that first. I don't think we have said that. So we have x is not equal to 0. Yes, great. Great. Now we did okay, we nearly are done. So now apply 1 times x equals m. Rewrites to m. So rewrite. Great. Now the other one. Uh-huh. I wonder if it's, I'm just gonna, my intuition is that something's wrong. Okay. Mole 1 says 1 times a. We need to reverse so we need to rewrite and do commutativity. Mole com. Great. Great. Okay, now we did the proof from the hypothesis to the a forward proof, the way we would probably do it by pen and paper, and we can do assumption. This closes the goal, and we did it.